All right, welcome back, everybody. Sustainable Engineering, ET210. I actually got the second lecture in. I'm very happy about that. Happy Friday, by the way. End of a long week, and I'm going to give you some things to think about over the weekend. This is our calendar. You can see the lectures here, and you have Solar Lab 1 due on the 6th. That's Monday. So, yeah, let's get into it. Just want to go through it fairly quickly. It's not too long. Hopefully y'all can see that. Looks like you can, so according to my screen. I might, well, let's see here. Yeah, I'm gonna put this down here because it's easier. All right, sorry. Here we are in our big blue planet. That's awesome, I have to say. The things we have to do here, we have to get in LCAs fairly soon, but we're going to move into the major renewable energy options and talk about those a little bit, starting with solar. But before I go into that, I'll talk about your individual project, because you have an individual term project in this class. So you need to start thinking about it. And by the end of day on the 6th, I'm going to want a proposal from you. So our top 10 environmental issues are climate change, energy, water, clean water, biodiversity of the planet, and our land use. So that's agricultural, logging, anything we use our land for that potentially is not sustainable. So those are the top 4. You can continue on with others that we're all familiar with, chemicals, air pollution, waste management's really big. Our garbage, our trash, the amount that we produce as humans and put into this planet is incredible. Anyway, so think about those when you start to brainstorm ideas about your individual project. So let's just talk about it. You can produce energy, or you can reduce a resource. Either one. You can be a producer or a reducer, okay? So think about that, like, okay, what do I want to do? Do I want to try and reduce my water use? Do I want to try and reduce my trash? Do I want to try to reduce, my fossil fuel consumption? Whatever you want to try to do, but I do want it to be quantifiable, meaning we have to be able to measure it, okay? And then the other one is you can produce. You can make a wind turbine. You can make a hydro system. You can make a on and on and on. You can produce energy. So you can make a generator. There's a lot of DIYs on how to make generators. And primarily in the US, that's how we create electricity, is by spinning a generator, right? A wind turbine does what? Spins a generator. Hydropower does what? Water falls, spins a generator. So coal-fired power plant, what's it do? It burns coal, which then in basic form creates a super hot steam, which then blows into a turbine and spins a generator. What's wave power do? Waves go back and forth, it moves a lever, which then spins a, yep, you got it, generator. Okay, so that's what I want. A producer or a reducer. If you're going to reduce, you need to come up with a plan on quantifying your current use. So you're going to go for maybe 1 week or 2 weeks quantifying whatever. So like if you're going to reduce, here's an example. If you're going to reduce trash, you need to go for a week at your home as a normal operation and weigh your trash, right? Or figure out how much there is somehow, right? And then in 2 weeks, you're going to adopt your reduction plan, and you're going to run that for, to the end of the term. Again, measuring the system, right? Determining if it's working, that kind of thing. And quantifiable is important to me, so we have to be able to measure it. But you can do that kind of a system with a lot of different resources. So come up with a plan. In the end, let's talk about production. So production, there's no pre-measurement, right? Production is just going to be, you're going to create energy somehow. And I want it to be you. I want you to make the energy, not, buy a kit off Amazon. You shouldn't have to buy anything for this project. So if you have questions about that, email me and I can go into deeper detail. In the end, you're going to assess yourself. So you need an assessment plan. Most of the time, that's a rubric. So a rubric gives points to achievement. So for instance, if I was going to write a paper and I wanted it to be 100 words long, my rubric could say, paper is 50 pages long, that's 1 point. Paper is 60 pages long, that's 2 points. Paper is 90 pages long, that's 3 points, and the paper is 100 pages long, that's 5 points, right? So that's just one piece of a rubric. Then you could go on about grammar, you could go on about paragraphs, you could go on about blah, 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 blah. So I want you to build a rubric, an assessment plan for your own project, your own iProject, okay? All right, so that's the individual project. Hopefully that makes sense to you. If not, reach out to me and we can chat, or I can call you, or I can produce another video if I need to. So if you'd like to see examples of other projects over the years, I can produce some of those and share them with you. All right. So let's go into renewables. Our top 5 are PV, photovoltaic cells. Those are the PV panels you see on the tops of roofs. Some of those are thermal, some of those are electric generators. So we'll talk about both, but PV, photovoltaics, is when the sun comes down, hits a solar panel and produces electricity, okay? We're gonna talk about that first, and then I'll just touch into solar thermal a little bit. But then we'll do wind, we'll talk about biomass and geothermal. We'll probably do hydro because it's very big in this area. And we'll do wave too, because wave's super fun. And also we have a lot of waves in this area, so we could be doing some stuff with waves. So yeah, let's go into solar panels. So PV panels look like this. And this is actually, each panel is an array of solar cells. So each one of these little squares is a solar cell. So we take a solar cell and we put it into an array to make a panel. And then we take a panel and put many panels into another array, okay? So you're seeing lots of these around the countryside now because it is a very good way to produce energy. But let's talk about that. This is a different kind of system. This is a solar thermal system, and these are not PV panels. These are mirrors. So you take a mirror, you direct the sunlight to a center location, which is extraordinarily hot, flashes a fluid to steam instantly, and then that steam can spin a generator. So these take up a lot more acreage, but again, require a little bit of less wiring. You can see there's no real wiring systems going between these, except for the wiring required to drive the motors to spin the mirrors to direct the sun to the focal point. So yeah, there's lots of different ways to do that, right? But renewable solar energy is based on a combinations of 2 phenomenons. One, natural, as the radiation coming from the sun, I'm going to move myself a little bit, is a consequence of these nuclear reactions in the sun, right? So it sends this energy to us. And the other is a result of our created technology that when the sun hits a photocell, it converts it to this current, right? And we've talked about current, we know what that is. It makes those little atoms in the valence orbit jump, right? So it's really cool how it works. And we're getting better and better at it, but we still are very inefficient at it. But let's just talk. So you did a thing with your energy at home, right? You looked at your bill, you calculated your kilowatts. Just as a basic example, I don't know what you came up with, but if your bill was $130, right? And we're paying, let's say we're paying 13 cents. I'm using those numbers because it's easy math. 13 cents a kilowatt, that would be 1,000 kilowatts, okay? So I don't know how many you came up with. in your calculations, but that's not uncommon to come up with a few different kilowatts. Maybe not 1,000. Let me do that again. Maybe it's 100. Yeah, probably 100 kilowatts. Let's see here. $130. And if I divide by 0.13, yeah, okay. So it's like 100 kilowatts, because 100 would be what? Yeah, it'd be $13. So if you're $130, that'd be 1,000 kilowatts. All right, that's a lot, but very possible, right? I want you to wrap your head around this number right here. 1.37 kilowatts per meter squared. Now, a meter squared is 3 feet. So you can't see it with my camera because I'm not wide enough, right? But a meter is 3 foot by 3 foot. It is a very small space. We get from the sun 1.37 kilowatts per meter squared. That's how much energy comes to this planet. That is an extraordinarily large amount of energy. We have enough energy coming from the sun to provide energy, electricity to everything that wants it times 10. Like, growth rate is covered by solar. The problem with solar is we're not that efficient at catching it, right? We don't catch 1.37. Matter of fact, 1.37 doesn't even get to the Earth because of dust, the atmosphere, and other losses. We typically get 1 kilowatt per meter squared, right? So that is still, it's an enormous amount of energy. And we use that number for calculations for installing solar. Now, do we capture 100% of that with our solar panels? Absolutely not. A cheap solar panel is about 15 to 20% efficient. So we get about 15 to 20% of that. An expensive one might bump up to the upper 20% to 30%. So we're really, really bad at capturing it. We just haven't figured out the technology to capture higher percentages that's still cost effective. We have solar panels that can catch a lot of it, but it's not cost effective. So they're not available. All right. But this is the first, one of the first things I'm going to have you do is, just so you know how many kilowatts is available from the sun, I'm going to have you calculate. You don't have to calculate your roof's square footage. All you have to calculate is the footprint of your home. So, for example, my home is 3,000 square feet, but that's in 2 levels. So the footprint is 1,500 square feet. Okay, with me? Now, 1,500 square feet is not square meters. So you have to do the conversion. That's about 500 square meters, but that's enough. I mean, that's close enough. Okay. So my roof's like this, which means I can only use half of that. So I can use 250 square feet or square meters of my roof. Okay. And then right now, I don't care if it's pointing in the correct direction. I just want you to get a feel for how much energy comes from the sun. So 250 square meters is my roof. That means I have 250 square meters, 250 kilowatts available per hour from the sun. That's a kilowatt hour, right? So if my roof sees 4 hours of sun a day, that's 1,000 kilowatts a day. Now, that's one of the cons of solar, is it's not daylight all the time. We only get that energy when it's daylight, and what else? When it's sunny, right? So we have to think about solar days, but I'm not having you go there yet. So what I want you to calculate is using the footprint of your home, right? Come up, you don't have to calculate trigonometry to get the slope of your roof. You can just use the footprint of your home. If your home has a peak, then you get half of it. The other half's not going to be very valuable. It'll be pointing the wrong direction, right? So use the footprint of your home, divide by 2, And then we're just going to use 4 hours of sun. Okay. And on a sunny day, we get a lot more than that. But we're going to use 4 hours. You can calculate for me how many kilowatts come to your home in a month. And let's say we have a sunny month. It's June, July, or August, where we get 30 days of sun. Okay. So calculate how many kilowatts come to your roof in 30 days of sun, only using 4 hours a day. Okay. So that was a lot. I can't really write. I don't have the camera, but you know, rewind it and talk yourself through that, figure it out. But that's going to be the home solar project, and that'll be up for you to submit. All right. I'm going to skip solar thermal. We'll come back to that. But let's talk about PV cells. And it's not super important that you need to know exactly how they work. But since we did have a conversation about electrons, right, let's look at it, right? So they're made up of semiconductors, right? Generally silicon, which is sand turned into glass, in which the effect takes place. This effect consists of transfer of energy, right, from the valence electrons. We know what that is now. So what happens is the radiation comes in, bounces the electrons into the holes that are created by these dissimilar materials. So you have a plus material and a minus material, and we want these electrons to bump over to, or actually, as we learned, it's going to go negative to positive. It's going to jump. And when we get those things jumping, that's current. Okay. It's not a lot of current, right? And it is DC current, not AC, but it's energy, and we can use it. It can get stored. Okay. So here's some percentages and different kinds. We have a monocrystalline, that's one kind of crystal. We have a polycrystalline, that's several kinds of crystals. The mono's 16% efficient, poly's 14. These are super cheap. Well, not super cheap, but they're cheap. And then amorphous is human-made crystals. And amorphous has got a higher percentage, but it's also much more expensive. Okay. All right. So here's an example. Unfortunately, these prices are not completely up to date, but it'll give you an idea, right? So here is a 80-watt panel. That's not kilowatts, that's watts. 80 watts, right? And here is the information about it. Notice that the amperage is very low, 4.54. Remember, amps is how much push there is, and there's just not a lot of push out of these things. But at the same time, we're getting 80 watts from it, from the sun. You know, it's just energy starts flowing out of these panels. So super fun, but not inexpensive. So here's a 4-pack of 265 watt panels. So these are a little more robust panels. But yeah, you know, near $300 a panel. So there you go. So on average, as we talked about in Portland, 1,000 kW per month is residential. So that would be a $130 bill at 13 cents. So you're going to start to look at numbers and you're going to start to say, oh man, I could go solar. Well, hold on, because we need to talk about solar days and our long, dark winters. Not as dark as Alaska, but they are long and dark. So there you go. All right. The other thing I'm going to have you do is some solar angle work. So this is the angle we're really looking for, and it can be called a number of different things. I don't think I have another slide. I don't. A lot of places call it the solar angle. Some call it the solar azimuth. This is a good graphic because this is the angle that we need, the angle from the sun to our location in comparison to the horizontal horizon. So from this to this is the angle that we are really interested in, because we want our solar panels to mount and be placed perpendicular to that angle. And what I'm going to have you do is calculate it. You're going to go outside with a stick. You're going to put the stick vertically straight up and down, and you're going to measure the shadow. So you know the length of the stick, you'll measure the shadow, and you'll do some basic trigonometry to come up with the solar angle. Note the time and the day that you do it, right? Even on a cloudy day, today's cloudy, even on a cloudy day, this can be done. You'll get a shadow, but you need a good flat surface. So try to find a flat horizontal surface. Try to do it at a time where the sun is nice and high, and stick your stick up, right? It'll make a shadow. Measure the shadow, know the length of your stick, and you can actually just calculate this solar angle that we're looking for. All right. Here's a little example of peak sun hours. So we talked about 4 hours, and this is from 10 to 1400. So that's actually 4 hours, right? That's some peak production in the solar curve of a day. But you do produce out here from 8 to 10 and 14 to 16. You're just not getting as much sun. So our number that we're talking about is a conservative estimate, but that's how they typically do it. They do 4 hours of production, even though you're going to get a little bit more. All right, so there's a couple websites that you can go and look up these angles after you do it. So that's fun. Inside of these here, I'll see if I can go to one of them. Maybe they'll work. And let's see if you can see this. I'm just verifying that you can see it. Oh yeah, you can see it. All right, so this is a fun one. You can input longitude and latitude of your location, and you can get those off the web pretty easily, or you can just put in a zip code. So I'll put in my zip code, 97030. Actually, that's the college's zip code, right? So once you do that, you can look it up. And it'll put it in there for you, right? And then we can pick a day. So I'm actually going to go with January 3rd. That's today. Is that correct? Yeah, that's today. Not 21. 23, right? And my elevation is about 400 feet in feet, not meters. So I'm going to put in feet, and you can put in any time you want. So I'm going to put in 12 p.m. So that's going to be noon, high noon, right? And then I'm not going to, daylight savings time. I'm not going to worry about any of that. I'm going to go calculate. So this is a fun calculator because it gives you some angles, but you can also, like, altitude angle, you can click on that and it'll explain it to you, right? And hey, look at solar altitude angle is the thing that we want. So you can choose our day. After you do this, you can choose our day and the same time and see if it compares. So 21.63 degrees at high noon at my location of Gresham, Oregon. Okay, so there's other cool fun stuff like the azimuth angle you can get. Azimuth angle is from south to where you want to put your solar panel, right? So it's like an offset. And then you can get some other really interesting pieces of information. Says the sun is setting at 4:41 p.m. So I think it's later than that. So I'm not sure if the daylight savings time. No, that's right. Time basis is clock time. I think that's right. Zero azimuth. It's probably supposed to be north. Yeah, I'm not sure why, because I think sunset's later than this right now. So I don't know why that's off. I'm gonna calculate again. Nope, same thing. All right, interesting. And then you can have like the input emailed to you. So use these after you calculate your sun angle. Go for it. These are super fun. So at least I think so. Yeah, back to PowerPoint, and I think that is the end. Yeah, there's just some more information about this and your lab. So, oh, the date is way wrong, so I'll fix that. But yeah, this kind of explains how I want you to do the angle. And it's due the 6th, not 1:30. I didn't here. We can fix it. We can fix it. Let's do that right now, right in front of you. So there it is. This is due 2.6. I think that's Monday, right? And then I wanted you to use the sun rays for today. So that's going to be 23. Or actually whatever day you do this on. So if I was going to do it right now, it would be 2/3/23. And I'd like you to use 12 p.m. or 11:59 a.m. That's fine, right? All right. But you can again choose your time. because you're going to do this whenever you can. I think I did this lab in class, so that's why I had them do an exact time. So this can be also your date, okay? But everything else is good. So I want you to, when you do it, I want you to go online and look up the same date. As you calculate. So, all right, that's it. Good luck. Save that, and then I'll post this up so you can get to those websites. Have a great weekend, and I'll do another one on Monday, and we'll just keep rolling through the renewables. Okay. All right. Have a great weekend.